All right, I'm going to kind of keep going where we're going. This chapter, and I've moved to Floyd. Did I make that book available as well? The Floyd book, right there. It's got a different cover to it than this one here. The book that I'm looking at right now is one that's what page are we on here? Right there. I don't want to. Is the one that looks like this one right here, Digital Fundamentals, and it's by Thomas Floyd, the 9th edition. That's an older version than the slides I'm using. The slides came out of the 11th edition. As you can tell, the slides and the book still match. So as textbook writers write textbooks, they change very little from edition to edition. It's a plot by the publishing industry to keep selling new textbooks. That's there. And I don't know if you buy textbooks here how much they are, but in the U.S. they're extremely expensive. This textbook probably in the U.S. sells for about $130, $140 US. That's there. So I mean, they're very, very expensive. And those of you that are going to Australia will probably find the same thing: is that the textbook industry in Western cultures is a complete rip-off, follows slightly behind the medical industry and pharmaceuticals. That's there. So that's there. So matter of fact, I taught a course at Unitin at one time where they insisted that we use a textbook that there was not an international edition. Purdue insisted. I was teaching for Purdue at the time. They were doing a 2+2, and they insisted that we use the same textbook as they did at West Lafayette or Indianapolis. And that particular textbook in the U.S. at the time was selling for about $85 to $90 U.S. And the currency crisis that we're experiencing now, this was during the one in the 1990s where the rate was about the same, about 4.2, 4.3. So as a result, the same textbook was selling for over 400 ringgit. That's there. So as a result, this 9th edition book that I made available to you that I found put there, if you were to go down and buy the full Western version, it'd be about 120, 150 US for the 11th. But I have the slides from the 11th, so the slides in the book don't necessarily match precisely, but they're close enough. But you do have this book, right? Because I'm going to have some reading for you out of this book before the next class. I want to talk about at the end of this class. We're going to have to go back to one of the previous chapters and cover 2's complement numbers from the second chapter that's there. So, okay, I'm jumping ahead here a little bit, and I'm into the 6th chapter of this book. So, as I said, and I know that it's a blur here too. But as we okay, too far. As we go into this book here, we're still in combinational logic, so we're still in chapter 6. We're going to be moving out of that in the next week or so, but there's some things we need to talk about out of this chapter. And the reason I need to go back to chapter 2 is that there's some things that I have to put on the final that are out of that chapter I skipped, so I need to go back and cover a few things here. All right, this is chapter 8. I want chapter 6. Okay. And we're getting counters. Okay, we're getting close. Okay. All right. Oh, chapter 5. I want to be Okay, the last thing we talked about, and maybe it might be easier if I just go to the slides right there. Right here. Oh, okay. All right, we went through the adders, the half adder and the full adder. So I think you have a very good understanding of that. We did a lab on that there. And we went through the process of building a 4-bit adder right there. So we built this in the lab we did this, it was last Thursday there, and everybody tested this. Some of you had some confusion on what it was doing, but you went through the circuit there. Now, this is a logic symbol of the 4-bit adder if we were to carry this farther right there. So as we look at the 4-bit adder, now this is a full bit 4 adder, and as we look at this right here, you can see that we have a carry in. Now this book uses C0 for the carry in right there, and C4 for the carry out. I don't necessarily agree with that notation but as you can see, this is so this particular book uses a different notation than what I used that doesn't say that I'm wrong and he's right, or he's right and I'm wrong. Different people use different notations, and that's what makes engineering fun, right? And it makes taking exams fun because you have to figure out what notation the instructor is using, right? Which is one of the reasons when you do take the final exam, you should read it first to make sure you understand what notations to use, because when we give the final exam, I'm required to sit in the room for like 10-15 minutes, and during that time is when you should raise any questions on the questions there. That's just a little hint I'll try to write it to where it's very clear, but I would probably use C in and then C out for carry in and carry out. I think that's more clear than C0 and C4. That's there. But I would use that. I would use C0. That's there. And I would use A0, B0, B4 there, or B3. I usually start my counters with bit 0 because that's the standard way of numbering. This particular author doesn't. And what makes it even more confusing is that chip manufacturers vary between chip manufacturers. So you look at one data sheet and it might say A1, A2, A3, A4, and another data sheet might say A0, A1, A2, and A3, and they're the same thing. So that's there. So as we look at these slides, this is the truth table for each stage. We went through this before. This is it. This happens to be a 74C283 or 74LS2. It's a standard 283. People in the digital world would say it's a 74XXX283. It's a 4-bit adder. This is an IC that you could buy off the shelf, or used to be able to buy off the shelf. You may have trouble finding it today, because a lot of these low-scale, discrete logic components we're going to talk about are not available off the shelf. However, they are available as block functions within Altera. In other words, if I go into Altera and I tell it that I want to put in a 74283, it would pull up this logic diagram right there. It would probably not show VCC and ground, but it would show everything else there. So, and as you look at this particular one, it has A 1 through 4 listed and B 1 through 4 listed. Now, I'm going to kind of jump out of here, and I'm going to pull up Altera just to, and I probably should put it on my, all apps, Altera. Put it where it's easy to find on my start menu, right there. That way I don't have to hunt for it every time, right? Because it is a program that I use a lot, at least when I teach this class. That's there. And I'm just going to open a new file. right there, just to simply show you what that chip looks like in the Altera, right there. And 74,283. So that's what, if you brought it up in Altera, this is what you would see. And as you see, Altera uses my naming structures for carry in and carry out, but they use A1, B1, A for that there. Now, it's kind of interesting, if you bring up Altera, depending on what chip it is, you may actually see what's inside that chip, that there. In this particular case, they don't, but that there. So, going back to my slides, right there, right here, this is the 74,283. You will be expected to know how to use this chip, right there. Now, if I put this chip on a final, I would put the diagram on the chip, right there, right there. In other words, I would expect you to memorize what a 283 is. This would show up as part of the question, right there. So, but there, what you see is on the left-hand side is you actually see, and my battery I think is dead. Yeah, okay, it does work there. Okay, but I'll use this here anyway. This is pin 1. If you look at the chip, that's the little dot. It goes around here, and the pin 16. There's VCC and ground are on 16 and 8, which is standard for 16-pin TTL parts. And you see there's all the various that there. If you looked at the Altera, you would see right there that they show the inputs on the left and the outputs on the right. And they don't show the symbols right there, but right there. So, again, back in the old days, when I say the old days, when I first started working as an engineer, we would buy these off the shelf, right there. Now, today, you'll be hard-pressed to find a vendor that sells these particular chips. But we still cover them because we still use them as part of the design process. Even though we're using software such as Quartus, we would still use a 74,283. Right there. And this is it doesn't recognize it. Okay, well then we can't use that. We will use the right there. So this basically shows the same concept that we did last week, that there. Only in this particular case, we're tying two 283s together to make an 8-bit adder. So it's the same basic concept as what we did before. Now there's no huge advantage in Quartus to use the 283 versus making your own 4-bit adder using, that there, or making an 8-bit adder out of the single 1-bit, full adders. In other words, if you need a 16-bit adder, you would just tie 16 full adders together, and you have a 16-bit adder. You can cascade 2 of those together to make a 32-bit adder. So you could do that fairly easy, but a lot of that there. Again, this is the same. And now notice something here, and this is kind of ironic. Notice they changed the nomenclature there from C0 and C4. Now they went to C in and C out. See, that's what, again, I said it makes life interesting that they've now, if I go back a couple of slides, right here, just one slide, you'll see that they show C0 and C4. Did everyone see that on the right side? And on pin 7 and pin 9. I go to this slide here, now they changed it to C out and C in. So, again, that goes back to my discussion. The fact is that a lot of times these pin numberings and pin names change from time to time, right there. So, that's there. So again, here they're showing 2 added up as a 4-bit adder. That's just, there's an 8-bit adder right there, and that's just the same thing as what I talked about a few minutes ago. Right there. This is just an example that they, and if you went to the textbook right here, if we went through in the textbook, I don't know what happened to our screen, it went blank there. There's an example. This is in chapter 6, right here. And this, again, this is they give an example on right there, and you can read that example. Basically, all it is we've got, you know, we've got people that are vote yes or no on a particular thing, and what this is doing here is we've got 2 adders here, 2 adders here, and we've got our parallel adder right here that we're going to add up right here, and this runs through here. We're going to talk about this chip here later on in this hour. So I'm not going to spend a lot of time going through this example right there. Right there. So read the example. That example could show up as an exam question. I don't think so, since I've already written and I didn't put it in there, but it's the type of thing that you would show up with. So, okay. Now this particular subject is something very, very important right there. And this is one of the problems with the method that we're using, is that we have propagation delays. I talked about propagation delays earlier, and that's the amount of time it takes before an output becomes valid when we change the input. It takes time for a signal to ripple through the circuit right there. So in other words, when I put 1 and 0 on here, this carry out should go to a 0 right there. Right there. It should go. Don't ignore this 1. This 1 is the amount of propagation delay. Is what that means. That's 1 propagation delay right there. There. So that there. So there's the amount of time before that there. And we'll say with the Altera software, that's roughly 8 nanoseconds. That's where this time came from. If we're using TTL parts, that might be 20 nanoseconds. That time changes as we go from one technology to the other. If we're using Altera, it's all on one chip, and there's about an 8 nanosecond delay as we go from one, through one adder to the next. If we're using TTL parts, it might be 20 nanoseconds. If we go to a very old TTL, it might be 30 nanoseconds. So if we go from an Altera to a full-fledged gate array, in other words, a fully designed chip, it might drop down to 2 nanoseconds. So this propagation delay is not constant between families and components. It varies greatly right there. And that's where the issue comes in, is that if you want circuits that are going to work all the time, every time, we have to figure out some way to get around this propagation delay. And the problem is that when we look at a 4-bit adder right here, is that we got 1 propagation delay before this carry out becomes valid. But then the next one can't calculate its output until it's got a valid input here. So it takes 8 nanoseconds before we change our inputs, before this output becomes valid. Then it takes another 8 nanoseconds before this output becomes valid. Then it takes another 8 nanoseconds before this one becomes valid. And it takes another 8 nanoseconds before this output's valid. So total, we've got 32 nanoseconds of delay. That's there. Now, that doesn't sound like a lot of time, but if you're talking about a microprocessor-based system that is operating at 1.5 gigahertz, that's a long time if you're talking about that there. So when we look at these adders, we want to try to shorten this propagation delay. And the way that you do that is we have what they call a fast look-ahead carry. We have additional circuitry within our IC that will calculate these carry outs much faster, so we don't have to wait for the propagation delays right there. So So again, we've got these propagation delays that they're, again, we're looking at the fact that each one of these causes that this slide doesn't add to there. So again, this slide doesn't add. But this is a logic. You do not necessarily need to know this logic. I'm not going to go through this logic in great detail. Welcome. All right, well, now, something going on? Everyone's running late today? That's there? So, remember when you get to Australia, some of the instructors lock the door at the start of class time. That's there. And they don't record the lectures, so what you miss is what you miss. So, keep that in mind, that there. All right. That there. This particular circuit is used for what they call a 4-stage look-ahead carry adder. So what this does is it looks at the carry in and it does a fast lookout that's there in order to get this carry out much quicker. That's there. Don't worry about all this circuit right here. This circuitry here is the same as what we've done before. That doesn't change. What changes is the fact is that instead of taking our carry out from here straight into here, we're doing an external circuit to calculate it along with here in order to calculate the carry outs much faster, so that we reduce those carry outs, the effect from 32 nanoseconds down to about 16 or 12. It doesn't get away from it completely, but it reduces the amount of time. In particular, it reduces the amount of time for this output one right there, the carry out, the one going out. It calculates that one much, much faster right there. So again, I'm not going to go into this, but you need to know what is meant by a look-ahead carry adder. You don't need to know the circuit, but you need to realize that this drawing right here causes a problem. The way we solve the problem is by having circuitry added to our chip that does the fast carry. And if we were to look at the book right there, as we jump down in the book here, it gives a lot more detail. Again, you can see this is the circuitry to look at our carry out is this circuit right here, or the time. So we come up with this combination look ahead right there. Now, I'm going to jump on to another subject. We are done with adders right now. We're completely done with adders. We're going to talk about a couple other circuits today. These are very common circuit. They're not as difficult to understand as adders, but they do have their place. And right here. Okay, first off, we have what's called a comparator. It compares two bits and says whether they're equal to each other. As it turns out, an exclusive NOR will compare two bits and say whether they're equal or not. If we got 0, 0, the output is 1. If we got 0, 1, it's 0. If it's 1, 0, it's 0. If it's 1, 1, it's equal to 1. So in other words, if we have an exclusive OR, that will compare two bits and give you a 1 output if they're exclusive NOR, if the two inputs are up there. So if we do 2 and combine them through an AND gate, it compares 2 bits and says whether or not they're equal to each other. So again, all we're doing is comparing two binary numbers and saying whether or not they're equal to. We can then combine those into, this is just an example where, there. We have a logic symbol that will compare two 4-bit numbers. This is, again, we're leading up to an IC that we can purchase off the shelf or pull off. This compares 4 bits. Now notice that we've got 3 outputs to this right here. Later on when we look at the chip, there'll be also the same inputs for cascading purposes. That's there. This is to compare two 4-bit numbers, and it will tell me if A is greater than B, or if A is equal to B, or if A is less than B. This is a 4-bit comparator. That's there. That is a circuit. That's there. And this is the chip board. It's a 7485. I could go to Altera and pull up the 7485 component. I'm not going to do that. I showed you with the 283 that it is in the Altera library. You just type in 7485 and the logic symbol shows up with all the inputs on the left and all the outputs on the right. That's there. And what you will see there is that it's got, as far as inputs goes, it's got A, which again, remember what I said a few minutes ago about how they like to change the numbering system? Here we're doing A0 through A3. When we did the adder, they did A1 through A3, or A4. So again, keep that in mind when you look at circuits, that when you're dealing with the 4-bit numbers, some publishers, some IC manufacturers will use A0 through A3, some will use A1 through A4. They mean the same thing, right there. So we've got A and B, they're both 4-bit numbers, and then we've got 3 inputs, A greater than B, B less than or equal to B, and A less than B. Did I say that right? A greater than B, A equal to B, A less than B. That's there. Now, if either the A greater than B or A less than B are high, then it ignores everything else. It just passes that signal on through. That's there. So the only time it does the comparison is if A is equal to B as the input is high. And we'll see that here in a minute right there. That's so that we can compare 16-bit numbers, 8-bit numbers, right there. This only compares a 4-bit number, right there. So this is basically what the circuit looks like for the A is equal to B. They don't give the circuit for the other ones. We don't care about the circuits. We're going to use this chip off the shelf. If you wanted to design the circuit, you could go back and use Karnoff maps and, look at all the various combinations. You'd have, that's 8 inputs, so you'd have 8. Oh, that'd be a mess. I don't recommend you try to design the circuit or worry about it. That's there. But this shows here that we've got, here's our least significant bits, A0 through A3. Here's A4 through A7, right there. We're comparing those there. Now, on the most significant bit right here, or least significant bit, excuse me, and I got that wrong, is that we're tying these outputs to here. So, in this particular case, it looks at this one only if these two are equal. So, the output, the most significant bit, I had that reversed up there. That's my mistake here. The least significant bit, you would tie A equal to B to 5 volts and A greater than B and A less than B to ground. Then this will look here, and if these are equal to each other, then it looks at this right here. If these two are equal to each other, then it looks at this. Otherwise, it will give the output there. So this is the configuration you would see for that there. So all this does is compare two 8-bit numbers and gives the valid output for which one is greater than that's there. It's a straightforward circuit that's there. And we can cascade these to 16 bits, 32 bits, 64 bits, however we want right there. But that's a comparator right there. So and again, this whole discussion here, and let me go back to the book and make sure I'm not missing something from the book. Right there, the book does the same thing. It looks at right here, at there, and it shows the chip, and it shows that circuit, and that's it. Now the next circuit we're going to talk about is the decoder. Now decoders are very, very, very important. Decoders, we're looking for a particular combination in order to get a valid output right there. And we typically use memory decoders for many, many purposes. In particular, we're going to be looking for a particular combination to select memory devices in microprocessor-based systems. So using a decoder in combinational logic is not commonly used. It is used for some cases, but its most common use is microprocessor-based systems. Right there. That is its most common use. Right there. So what this is doing right here is this is looking for a particular combination. And this looks like the same thing we would say for a product of some circuit right there. Product of some circuit right there. This is looking for the combination right here, A3, A2 naught, A1 naught, A0 right there. It's looking for that combination going into that there. Any other combination will give us a 0 output. Now there's nothing magical about that particular circuit right here. Again, this is just an example. Now the 4-bit decoder is one that is much more useful. It has 4 bits into it, and it has 16 outputs right there. Now this happens to be an active low. Most decoder circuits are active low. And let me kind of get off on a sidetrack here. Go. Quick one note. Right here. Is the reason we see that is that when we look at a microprocessor system, we have, here's our microprocessor right there. And we haven't talked much about microprocessors, but a microprocessor has coming out of it something called the address bus, A0 through A15, for example, right there. This is 16 address lines. And that's very common for an 8085, 8051 with external memories, that there. Well, each memory device will access so much memory right there. And what we normally will do is we will take, say, for example, A15 through A11 and use those to decode the 16 different memory devices that we have. So this would be memory location F, 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 F. This would be E to F000, E, F, 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 F to E000, and on down. In other words, we have 16 different memory devices attached to that. And that's an extreme case right there. We have 16 different memory addresses. So we need this device to look at A15 to A11 and determine into our chip select not pin. Most microprocessors use active low chip selects. And the reason it uses active low chip select is because the noise immunity is greater there. You have between 0 and 1.8 volts, or 0 to 0.8 volts for a ground, to ensure that it's 0, where you can have from 5 volts all the way down to 3 volts for something to float high. And things tend to float high in microprocessor systems more than they float low. So using ground is a more stable use right there. So they typically use active low right there. So, and that's the number one use for decoders. There are other uses for decoders too. We'll look at that there. But the number one use is microprocessor-based systems. And because microprocessor-based systems have active low chip selects, that when we look at our right there, when we look at our inputs here, A00, we'll see that this output, the corresponding output, is a 0 right there. Right there. And if we look at, say, the binary number 91001, that corresponds to that there. That means that our ninth output is going to be low. Everything else is high. Right there. So that is a decoder. Right there. Now we have other uses for decoders, but this is the most common use for a decoder. Right there. So as we look at right here, this here, right there, this is the same table that I looked at that there. So this is what we're using, and we have other uses for it, but you need to know what a decoder is. Right there. There. So keep that in mind, that this is a circuit that you need to know that truth table, and this happens to be the logic symbol for it. This particular one happens to list over here our values, but this is our A0, A1, A2, A3. And sorry about my handwriting being bad there. I'm trying to write over the keyboard right there. But those are our inputs. These are selecting, this selects a particular device. Now, we can use these for other things too, such as, for example, we want to select a particular telephone in a system, or we want to select a particular device in a multimedia system right there. So these can go to our select pins to our particular devices. Say we have 16 lights we want to turn on. We want to turn them on one at a time. We can put a counter and generate a counter, light one light at a time, for example. There's lots of uses for it there. The 154 is a 1 to 16 decoder. It's a chip, just as we talked about. That there, I could pull that up with the Corda software and get a symbol that will look something like this. Now, something about this particular chip is different, is that we've got two additional inputs that are not accounted for. And these are chip select knots that are ANDed together in order for this chip to even be selected. If those two inputs are not both ground, the output is all the outputs are going to be high. This chip is not selected. If you, right there. So they show, for example, here, they don't show the truth table for it. But if those are not both high or low, then everything's going to be high on the output. Now that's used here, for example. Here we generate a 32-bit decoder where we've got 0 through 31 outputs. We've got 5 input pins. Right here, 5 input pins right there. We use the 5th input pin, A4, is tied to this one right here. And notice that these are knots right there, chip select knots right there. So if A4 is low, then this one is going to be selected. So if A4 is equal to 0, this one is selected. And the reason I can see that is because I'm tying it to chip select right there, and I'm just tying it to both inputs. Now, if we could do 4 of these and have multiple, we can make this more complex. And then we run it through an inverter, so if A4 is high, this one is selected. So now I've got a 32-bit decoding system right there. A 5 to 32-bit decoder. And that's actually, you'll see this is a 1 of 16 decoder. This here is a 1 of 32 decoder. Or a 5 to 32, a 5-bit decoder circuit there. So again, we're looking at this right here. BCD decoding, again, is the same thing, only they just go 0 to 9, right there. This happens to be another chip, a 7442, that has 4 inputs and 9 outputs, right there. So that happens to be a very common particular. Another place we use these decoders, by the way, what we're going to see is when we do multiplex displays. That there. If we want to select multiple displays, that there. So again, this is just showing, this is just simply a counter that counts from 0 to 9, right there, and then our output, you know, when they're all low, the output, that's 0, when it's 1, this actually just shows the same information as this right here. Right there. So BCD code, this is our input, our decoding, and these are what shows us the output right there. Okay, now, this is a little bit different device. This is a 7447. And we're talking about a lot of different devices today, a lot to remember. Please go back and review these slides before that's there. Please read this chapter in the book. It's not a very difficult chapter to read. I know that English is a second language. Hopefully you can understand the English. You've been selected to go overseas to study in an English-speaking country, so your English skills better be better than some of the ones I've seen, right? That's there. So, unfortunately, you've got the task of understanding me that speaks fluent English, sometimes very fast. By the way, I've tried to slow down. Am I speaking slow enough for this group? Some people say no. That's there. I know you got the recordings to go back to for that reason, but that's there. You know, if I do speak too fast, say slow. Just stick your head up and say slow down, please. Okay. All right. Getting back to this. This is an input here that is 0 to 9, and these drive the LEDs on a 7-segment display, right there. I don't know if the slides show a 7-segment display. They show it here, but they don't show that there. Let me bring this up here. When we look at a 7-segment display, right there, right here, everyone's seen these. They're old technology. They've been around forever, right? That's there. A, B, C, D, E, F, and G. Sometimes you'll have a decimal point in front or back. That's there. So sometimes you may have 9 inputs there. Typically, 7 is the normal, right there. So if you want to display the number 2, for example, you would light the A display, the B display, the G display, the E display, and the D display. Everyone has seen these right there. And a BCD, the 7-segment decoder, does exactly that for you. These have been around so long that I remember when I took my professional engineer's exam, I had to design a decoder for the E segment. That was one of the questions on the professional engineer's exam, where then I had to come up with a truth table for it from 0 to 9, and then do the Karnoff map. That there. But that's all done for us. But this is a 7-segment display, is what this is. The 7447 is a standard that I didn't even have to look at that. It's been around for a long time, right there. And we've got our inputs, our BCD inputs right there. Again, these are A0 through A3, if we want to use the number A right there. This is the byte bit count. That's the 1 bit, the 2 bit, the 4 bit, the 8 bits is what we're using. We've got our blanking inputs there. We'll talk a little bit about those there. We also have an output that's for blanking leading digits is what that's for. If we have leading digits, we want to blank right there. So in other words, if you got a speedometer on your car, for example, that goes from 200 km to 0 km and it's LCD and your speed is 65 km, you want to have 0, 6, 5, or you want to have just say 65 right there. We want to blank out that leading 0 is when we talk about blanking the leading 0 out there. So this is a very common. Now note that all these have ground right there. It depends on the 7-segment display that you have. Most 7-segment displays are designed where all the cathodes are connected. I think that's the cathode, right? Right there. These are light emitting LEDs right there. Right there. They're designed, and we got A through G right there. They're designed. That's what's inside the 7-segment display. And then normally we would put on there externally a resistor right there. Now depending on if this is 5 volts, that's normally 330, 220 if it's 5 volts, or 3 volts, depending on what the output is. That's there for the display, in order to get the right current in order to light our LEDs. If you don't put that there, and then these is now then connected to the 7447. That there. So if you ground this pin, you turn on the LED. So when we look at a 7-segment display, if you ground the pin, it turns on the LED. There are some displays that are wired the reverse, where you have to have a high output right there. 90% of the ones I've worked at have been this type right here. Actually, I think it's common anode. I keep getting those confused because I don't use the terminology very often. But when we look at the diode right there. So as we look at this here, notice that we got the bubbles there, right there. And those bubbles basically means that it's an active low output. If we take the G output low, we light the G LED on the 7-segment display, right there. And I'm going to revert back to the book just to make sure I'm not skipping something that he covers in the book. He gives the example right there. And he gives an application here where, again, we're selecting various monitors right there. Right there. Again, notice that he's using a microprocessor here and say what port do we want access right there. And here's our I/O request right there. Again, read this after. And that's the same circuit that we have there. And I'm just looking to see whether he doesn't do any better job of showing a 7-segment display than what I did. Matter of fact, he didn't even show that there. So, okay. So basically, when we look at this right here, this is our typical display setup right here. Notice that we take this output and we drive it to this here. We blank these two displays right there. So we're suppressing the leading zeros right here. Here we're going the opposite direction here, and we're blanking the trailing zeros right there. It just depends on the application. usually you're going to blank leading zeros. That's the normal case, right there. So, but if you want to blank the trailing zeros, you have the case. So if you look at this right here, these are 0 inputs, so there's no reason to show them. In this particular case, our speed is 30 kilometers an hour, right there. If we're using it as a speedometer. But again, we're just tying this output to that output. And we could do this as many digits as we want, right there. As many digits as we want. So this is a 7-segment BCD to 7-segment decoder. It's a 7447. They've been around for a long time. They're still being used. Typically, though, again, you're using programmable logic, so you would just pull it off there. So now, one of the things that this is the logic symbol for digital input, BCD output. This is actually a decimal to BCD encoder. This particular case, we've got 10 inputs, and we've got a BCD output. And what this is going to do is if this output is high, then I'm going to show 0, 0, 1, 0. I'm going to tell what inputs are high, if any, right there. So that they're usually priority. When I say priority, means that if there are 2 inputs that are high at the same time, then it's going to show that particular number on the output right there. Because I can't show 2 outputs right there. So I'm going to kind of skip through this particular one right here and go straight to the 147. Here's the 147 right here. And this particular one here, again, these are active low. And by the way, expect a test question that says, what's the difference between active low and active high? Right there. And all this is going to do is I've got 10 inputs, and whatever the highest one that is low, that number is going to show up out here. Now this is used, for example, if you've got multiple equipment that fails, for example, and it's going to take an output low. In other words, that piece of equipment fails. That tells me what my error code is, right there. There's multiple other places that we would use this for, right there. So again, this is, for example, a push button decoder. This is not a typical push button encoder, by the way. We would never use this because it takes 9 inputs. We usually use a row and column, and we'll talk about that later, right there. But I've got 9 buttons here, right here, and whatever button's pushed, that number is shown on the output right there. But notice that it's an active low output right there, which doesn't make that much sense right there. But again, right there. So again, binary representations, right there, I'm going to skip. Here we're getting into BCD numbers. And we didn't really talk a little bit about BCD numbers. BCD is a code, it's not a numbering system. Right there. And we often want to convert data from binary to BCD before we display it. The reason is if you got a speedometer and your speed is 3e, you want that to show up as a base 10 number. So we would run that through a BCD or a binary to BCD decoding circuit right there in order to get the right number. Now, if you're doing with a microprocessor, there's a command called BCD, adjust, right there. So, again, basically, I'm going to skip the gray code converter right there. Let me talk a little bit about the gray code, because we did use it a little bit right there. The gray code is a code that only 1 bit changes at a time. An example of that is 0000, 0001, 0011, right there, 0110, or excuse me, 1, and we could go on through here, but notice that we go to 111, and then we go to 1110, 1100, and we go through a particular code, you know, right there. And we did that when we were doing the 00011110, and the next one is 00 right there. We'll just look at the 2-bit counter right there. And you can come up with a 16-bit gray code, which I was going to. It's just going to get too messy, and it just repeats right there. And it was very popular for a long time for what they call encoding rings. An encoding ring is a ring that looks like this, and you've got 4 black and 1 here, and then you've got 1 shown here, then 2 shown here, and the whole idea is it's to see what your position is as you rotate the wheel. And it prevents errors because if 2 bits change at a time and they don't change exactly at the same time, you end up with a situation where your number is 00 and it's supposed to go to 01, and then from here it's supposed to go to 00. But between here and here, it may go to 00, then 10. Or it may go to 11, then 00, depending on which digit changes quicker. See, because both these don't change exactly the same time. So you have an error condition, a glitch. So the reason that they used the gray code was to prevent glitches, right there. And it was very effective. Not that many decoding rings, you know, where they use the optical systems to decode are used that much anymore. There are still a few. The gray code is not that popular today. You saw it when we did the Karnaugh map because that enabled us to eliminate, you know, you only change one input at a time. Right there. So, the 4-bit binary code conversion right there, we take a binary in and it gives us the gray code out. It's a fairly easy converter. All it is basically 4 exclusive ORs is all it is right there. Right here, and it shows that 1010 going in, 1111 is what comes out of that there. 1001 comes in, we get the binary right back out. It's actually one of these strange circuits that to convert to one to the other is the exact same circuit right there. So again, right there. Okay, now I'm getting into one of the most important circuits, and we're going to spend a little bit of time. We'll probably finish up with this circuit and look at some circuits using this to do Boolean expressions that are probably not covered in the book, but that there. This here is used to select which one of these goes to here. S0, S1, if it's 01, that's the number 1. That means that this input is tied to here. If it's 11, then this input is tied to there. It enables me to select one of 4 inputs to go to the output right there. This is a very, very functional circuit. It's used for many, many applications right there. And it allows us to say, for example, this is the multiplexers. There's another circuit we're going to talk about called the demuxtiplexer, which does the opposite right there. And let me just kind of give an example before we get into it right here. We have a mux here. It's got S0, S1. We've got 4 inputs to it, D0 through D3. We got one line coming over to here. This is the demux. We haven't talked about the demux, but we'll talk about it in a minute right there. We've got 4 outputs here, S0, S1, S2, or not S, we'll use D0 through D3 right here, D1, D2. And we also have, and I'm going to erase these and put them down here. S0, S1, S0, S1. We're going to tie these together right here. What this allows me to do is select one of these inputs and send it over to here. Then select the next input and send it over to here. So now if I have a 32 channel, for example, means that I take 32 lines here, and I'll need 5 select lines there, and I can reduce the number of lines for communications. So I can connect this device to this device. That there. Now I can also break this apart and take this device and select it to another device over here. So I have one selection here, and then I have another selection there, and I can route data however I want to route my data. That's there. Very, very powerful tool right there. So as we look at this right here, basically all we're doing is we're selecting which input is sent to the output right there. Right there, 4-to-1 multiplexer, and all we're doing is, it's a very simple circuit. We just tie our, right there, and this one here is, both these inputs are high, right there. This is 0, 0, because I'm taking this off the NOT line, and this off the NOT line right here, off the 2 NOT lines. That means 0, 0. This means that 0, 1, 1, 0, 1, 1, and that's what's selected out there, right there. It's a very straightforward circuit, but it's a very powerful circuit in terms of reducing wiring for data communications. We use it a lot right there. And again, what we're seeing here is that as we go through here, we're D0, D1, D2, D3, D0, D1, D2, D3. So we're selecting which data that we're sending out right there. These were used a lot in telephone switches. They still are. Most people don't realize that the old analog telephones were actually multiplexed. You didn't have one wire that went from your house to your neighbor's house across the street. You had one wire that went from your house to a phone switch, and then you had a couple of thousand wires that went from one phone switch to the next phone switch. So it would go through and it would select which wire went to which phone on the other end. These were telephone switches. They were completely multiplexed. So these have been around since the invention of the telephone switch right there. Matter of fact, one of my first job interviews that I didn't take the job, unfortunately. Actually, who knows what my career would have been, was with AT&T or Bell Labs that designed phone switches. That's there. So I got during the job interview, I did a lot of study on phone switches and how they operated. That's there. I was offered the position, I ended up not taking it. That's there. So, but telephone switches use a lot of multiplexers and demultiplexers. Those have to be used to be analog multiplexers, demultiplexers. Now they're digital switches. Right there. So they're very, very commonly used. We can also use them to implement, for example, there are the demultiplexers, and we'll talk about the Boolean, using them for Boolean expressions later here. So again, we're looking at right here, this is a dual 4-bit multiplexer. It's the 153 right there. And we've got two of them on the same circuit. Notice that we also have a chip enable on each of these. These are our 2 enable pins. These are our 2 select pins. So we can select one of the 2 right there. We have 2 outputs right there, or we can select both of them. In other words, we can do 4 at a time right there. So we also have the 8-input multiplexer. Again, it's got 3 to 8. It's called a 3 to 8 multiplexer. We've got our 3 select lines, our enable line, and then there's our 8 data lines coming out or coming in. Also note that we have both active high and active low outputs. That's something we haven't seen before. Right there. Again, this is a standard 16-pin switch. Quartus carries it directly within its library. That's there. So, right there. Here we've got a 16-bit right there, where we go through and notice that we use the enable line here to deselect that one right there. So, and we're using the Y not on both of these, but we're using this through a NAND gate or AND gate right there. In other words, we're using this here. If S0 or this should go to S4 for S3, excuse me. If S3 is low, then it's tied directly and that multiplexer is selected. If S0 is high, S3 is high, then this one is not going to be selected because that's going to be high, and this is run through an inverter, and this one is selected. So now we've got a 16-bit multiplexer out of two 151s right there. So it's a fairly straightforward, and then we use, this is actually a NAND gate right there in order to select what our output's going to be right there. Right there. So if this is not selected, then this output has to be high. The Y not has to be high right there. So again, we're looking here at a simplified. This is the more common way of doing this. This is our common cathode tubes right there. And here is our multiplexer. What we've got here in this circuit, and this is and I'll probably wind up after talk, we'll see what else I've got here. But this has got A0 and A3 and B0 through B3. These are two separate digits that we want to show right there. We want to show B0 through B3 here. This is B. We want to show A here. Right there. Everyone clear what I'm wanting to do? I want to use only one 7447. Right there. So I only want to use one 7447. Right there. And the way that I do that is, again, keep in mind that this is set up right here internally. Now, they don't show the resistors here. We would have to have the resistors shown here. But here is the diode there. I'm showing a resistor here, right there inside that they're not showing the resistor pack right there. And these are tied to where if I apply the ground, I turn that 7-segment display on right there. So I'm applying the ground to turn that on right there. Now what I've got here is that I've got a data select that first, if this is ground, then I'm going to tie this one to ground. If this is high, that one goes high, this one goes to ground right there. So I've got a clock here that goes high, low, high, low. When it's low, input A is selected on these mux right here. Input A is selected on the mux right there. Right there. So when input A is selected, that goes to the output A. Here, input A is selected, that goes to this output B. Here, A2 goes here, A3 goes there. So when my, what did they call this here? Data select. So when data select is equal to 0, A0 goes to A, A1 goes to B, A2 goes to C, A3 goes to D, right there, on our BCD to 7-segment display. When D0 is 1, or data select is 1, then B0 goes to A, and like that there. So it selects either number A or number B. Now, down here on my decoder, when A is selected, I take this one to ground. When B is selected, I take this one to ground, right there. So first I turn on this display, then I turn it off and I turn on that display. Then I turn this display on and I turn this one off. And I keep alternating between the displays. Now this doesn't look like a lot of savings because I've only got 2 displays. But if I've got 6 or 7 displays, that saves a lot, because typically this here is actually coming out of a microprocessor right there. But if we have multiple devices digits we want to display, we would multiplex the display data and go through and turn on one display at a time. So if I had 6 displays, for example, I wanted to use right here, and this is A naught through G naught on each one of these, they would all be tied together right there. Right there. All would be tied to 174.47. A naught, G naught. Oh, that's there. They all would be tied together. And then my chip selects would then be taking, I would ground this one right there. At the same time I ground that one, I would put the data out for that particular display. Then I would ground this one, I would put the data for that's the display. So when you look at a 7-segment display, they're not all on at the same time. They look like they're on because we do this at a couple kilohertz. And it's so fast that you can't see it. You could actually slow it down to about 100 hertz and you wouldn't see it. But if you slow it down enough, you could see one display coming on at a time. And it saves a lot of wiring, especially when we get into microprocessor-based systems. That's there. It saves a lot of wiring. And this is the standard way that we drive 7-segment displays, right there. So going back to our PowerPoint, this is just showing it for 2. Notice that we've got just a single dual. This is a dual. And remember, if we go back to our previous slide, we talked about the 153, the dual input data select right there. This is the reason for the dual input right there, is for this particular purpose right there. Right, here's our 8 if we want to do 8. Right there, same thing. Right there. And also note that we have here Y and Y not, so if we had the other active high output, we would normally not use the active high output there. That's there. So again, what we're looking at, here's our inputs. I'm not going to go through that. That's there. Data select is the logic. I will stop here at this point because I want to go through this in more detail here, because what I want to talk about is how to use a multiplexer to generate a 4-input variable function right there. Right there. So it's a way of doing that there where we want to, this particular one here, well, let me just talk a minute about it. We've got a few minutes here. What we're looking at here, this particular example is we're going to take a 3-input function, and we want to generate this truth table right there. Right? So we've got our 3 select lines, A0, A1, A2, right there. So we're going to do that, and all we do to do that is we use A0, A1, and A2 as our input variables right here. Those are our 3 that we're going to select A0 through A7, or our inputs there based on that there. So if we go back to our truth table, any place we want a 1 right here, 1, 3, 5, for example, and 6. Going back to our truth table, 1, 3, 5, and 6, we tie it to VCC. Every place we want it to be ground, we tie it to. That's there. And it's a way to implement this Boolean expression without doing any and or gates. Right, that there. There's a better way of doing this if we want to do a 4 input, and I will start the class next time with that there. So, right there. Matter of fact, he goes through and he shows that right there. I will start that there. I'll start with this on Tuesday, right there. I think I've covered a lot of different components today. So today is just knowing the components. Really no circuits involved. Tuesday we'll get back to some circuits right there. So I want to go through and finish this chapter on Tuesday, and then I'm going to backtrack and go back and cover ones and twos complements on binary numbers. Right there. I'm going to go back to binary numbers for a little bit on next Tuesday. Right there. And hopefully we can get to a lab next Thursday. Right there. So do we have a holiday? No, there's no holiday next week, right? There's a holiday in what, 2 weeks? I think it's on a Wednesday, isn't it? So you guys don't get a day off, right? So, okay. With that said, let me stop. Yeah, an hour and 15 minutes is about what I'm good for this class. That's there. Actually,